Hi everyone, today we're going to be talking about topic 8.6, molecular structure of acids and bases. And so the entire purpose of this topic is just to think about what the structure of an acid is and whether or not that affects if an acid is strong or weak, or if a base is strong or weak. And really, structure can help us determine whether or not something is an acid or a base. And so there's two big factors that really determine the strength of an acid. One is bond strength, and the second is the stability of the conjugate acid, A-. We'll go with bond strength first. Generally, the weaker the bond, the stronger the acid. And so we have to think back to our periodic trends here, but bond length, and we haven't covered this too much, but I'll give you the basic gist of it. Bond length is determined by atomic radius. In other words, the larger radius equals longer bond length. You have to remember, if we think about the periodic table, as you go down, radius increases. As you go across, radius decreases. And so the larger your conjugate acid, or the larger that bond is, the weaker or the stronger of an acid you're going to have. The reason why is, if we think about the equation that's happening here, we have HA plus H2O. That makes H3O plus A-. This is aqueous, aqueous, and aqueous. Let's compare it, for example, to this one, where that's a longer bond. I'm really exaggerating it here so you see what's happening, but let's compare it to the case where that's a much longer bond. In the longer bond case, it's easier to release H+. And so the weaker the bond, the stronger the acid. The second thing that determines stability, acidity, is the stability of A-. So again, I'm going to draw out this reaction because it'll help us see what's going on. If we have HA plus water, we get H3O plus, and our A-. This is what we're interested in this case, our conjugate base. If this is really stable, in other words, it likes being on its own without the H, the reaction wants to go to the right, which makes it more acidic. And so the more stable A- is, the stronger the acid. And this is the exact opposite case for bases, right? A really short bond will make a better base, whereas a really unstable conjugate base will make it a better base. And so I have this helpful thing here that at least helps me remember, whether or not something is a strong acid or base, and it's called ARI. So A means atom, R is something we call resonance, which I'll explain in a second, and I is induction. These three can really be used to determine if something is a strong acid, is a stronger acid than another one in most cases, especially if we're looking at weak acids. And so when it comes to atom, the important thing to think here is the larger the A-, the better the acid. So let's take the case of H2S versus H2O. If we look at our periodic table, O is directly above S. S is a larger atom, and so if we look at our conjugate base here, this is HS minus versus OH minus. Because this is a larger atom, this one is the stronger or the more stable, it's the more stable conjugate base. Therefore, because it's a more stable conjugate base, it is a stronger acid. And so look at the atom and see what it is. If you're comparing sulfur to oxygen, things that have a hydrogen that is bound to a sulfur is going to be more acidic than a hydrogen bound to an oxygen for that reason. That same case goes for, chlorine or bromine or iodine. The next factor is what we call resonance. And this is something that you learn much more in an organic chemistry class, but I'll introduce what it means right now. Let's say I have this molecule. Which is known as acetic acid, otherwise known as vinegar. Right? And let's compare it to this molecule, for example. Which is methanol. Once I take away this proton, right here, and right here, what I get is this. And I get this. Right, I basically take away that proton, I end up with an O-. Resonance basically says that if your negative charge can move around, the conjugate base is more stable. So therefore, it is the acid is a stronger acid. And so let's look here, for example, right? My negative charge here, it can stay on the oxygen. It can go to carbon, but carbon's not really electronegative, so it doesn't really want that. But if we look here, right, this negative charge can just move over there, right? Those two oxygens are equivalent. And so we can have this case where my negative charge, right, it's just a pair of electrons. It moves around. And so now I have this. And so because I can do that, this is more stable. And so you got to look out for, in terms of the structure, right? If you're given a structure that looks like this, where you have these, what's known as a carboxylic acid. This is a carboxylic acid. I'm going to highlight it in green. This sort of little group here. If you ever see that, it's going to be more stable because that negative charge can move around. Whereas here, right, it's stuck there. The negative charge is stuck. So it's not going to be very stable. Okay, that's essentially resonance. The third in RE is called induction, and I'm going to do that down here. Induction. So let's say I have this case. Let's compare HiO4 versus HClO4. Induction, this has to do with electronegativity. And so let me draw out what these actually look like. I have I. That's HiO4, and HClO4 looks like this. Sorry, let me draw out this bond as well. So if you're given structures that look like this, if we're trying to compare which one is stronger, we need to look at their electronegativities. Now what we know is that Cl is more electronegative than I. And so Cl pulls more electrons. And so now I encourage us to look at the conjugate base. right? Essentially, in the conjugate base, all you do is you just remove that. So the conjugate base of this is, and the conjugate base of the chlorine is the same thing. It's just you have chlorine instead. So now what's happening here is that my chlorine really wants to pull those extra electrons that are on the oxygen, where my iodine, my I, really doesn't want to that much. And so because of that, this is more stable. So the general rule here is if you have an electronegative atom near an acidic proton, it's a stronger acid. So when we're thinking of strength of acids, I want to just summarize once again, because I know this is a lot of information. We need to think about two main principles: the strength of the bonds, so whatever is bound to my H, that bond right there. We typically think about this when it comes to binary acids. So think, right, HF, HBr, HCl, HI. And the other thing is the stability of A minus, the conjugate base. So you normally want to think about this when it comes to most weak acids. And that really depends on things like the atom H is attached to. Think about size and electronegativity. We need to think about resonance, like I explained previously, and induction. So we really, and I'd say the biggest thing you should be thinking about is electronegativity in this case, because that really does a lot towards the stability of A minus. But the more stable A minus, the stronger the acid. That's the basic takeaway there. Now, another important factor when it comes to bases are what are known as the nitrogenous bases. This essentially just means nitrogen, right? And so substances that have a nitrogen usually have the property of bases. And so these are bases that you actually find in DNA and RNA. But a base that you'll most commonly see here, right, is NH3. Right, NH3. This is a common base. And the reason why is if it has a lone pair, right? If you draw out NH3, and we can talk a little bit more about Lewis structures in class as a refresher, right? It has that low lone pair. This can essentially take a proton from an acid, and it'll make NH4 plus. Right now, it no longer has a lone pair. And so we need to think about, and you'll typically be given a structure with this, right? Does your N have a lone pair? If it does, well then great, it's a pretty good base. If it doesn't, then likely it is not a base. In this case, NH4 plus, this is an acid. NH3 is a base. So let's look at this one practice problem together from AP Classroom. And so this shows us 3 different particle diagrams, 1, 2, and 3. Let's first read the question, then we'll go back over to those diagrams. So it says, based on the information, which particle diagram best corresponds to the indicated acid? And so we're trying to match these diagrams to these 3 acids, HClO, HIO, and HBrO. And so now let's look at the diagrams. In diagram 1, it looks like it's partially dissolved. The reason I say that is because I have some HA and some A minus. But I still have, right, I have both of those in there. But it looks like it's mostly, if not halfway, dissolved. In diagram 2, this looks like it's barely dissolved. Because let's look. I have 1, 2, 3, 4, 5, 6, 7 HAs, and I have 1 A minus and 1 H3O plus. So I'm barely dissolved. In number 3, we can see that I'm mostly dissolved. Because I have a bunch of A minus in solution and barely any HA. And so if we look here, we can think about the strength of these 3 acids. HClO, that looks like this. Oh, sorry. HIO looks like this. And HBRO looks like this. And so the main thing we need to consider here, right, is the strength of this bond, as well as the stability of A minus. If I lose my proton, I'll look like this, and this. And so now this one's a little bit tricky, right? Because it doesn't exactly tell you which diagram you want to look for, but there's a few hints here. What we're looking for in this question is which is strongest and which is weakest. And so if we look here, what we need to think about is induction. In other words, higher electronegativity equals stronger acid. So if we look at our periodic table, we should see that this has the highest En. So this is strongest. This one's in the middle. And I, because it's further down, is the weakest acid. We got to remember what the definitions here mean. Strongest means most dissolved. Weakest means least dissolved. And in the middle means in the middle. So given that information, what we need to do is match the strength to the diagram. So now let's go back to our diagram. Because ClO minus, or HClO, is our strongest, this one should be the most dissolved. HIO should be the least dissolved, and HBRO should be in the middle. So let's go through each choice and see if it actually makes any sense. So choice A says diagram 1 corresponds to HClO. If we look at diagram 1, this one's half. So this one should be HBRO because it's halfway, just like how HBRO is in the middle of these 3. So A can't be our answer. Let's look at 2, or B. Diagram 2 corresponds to HClO. In this case, we know that diagram 2 is the least dissolved. It's barely dissolved, and HClO is our strongest. So it can't be B. Let's look at C. It says diagram 2 corresponds to HIO. This makes sense. HIO is our weakest. Diagram 2 shows the least dissolved, so that should be weakest. So that answer makes sense. But just in case, let's look at answer D. Diagram 3 corresponds to HBRO. Diagram 3 is mostly dissolved. Because it's mostly dissolved, this is strongest. This one should be HClO. So D doesn't make sense either. And so the problems relating to this particular topic are thinking of this. It's analyzing what a diagram looks like or a given piece of information of whether or not something is strong or weak, and then thinking about structurally how that looks. We'll talk about this more in class so we can get a better sense of this and talk a little bit more about the Lewis structures involved in doing these kinds of problems. But for now, that's all. Thanks, guys.